In this video, we're going to be doing hypothesis testing. We're going to be going through hypothesis testing examples, and we're going to use Rguroo as our technology. So we want to first start by reviewing the steps for hypothesis testing. The first thing that we do is we need to identify what the claim is. So the claim is often a belief that something is different than what we have always assumed it to be. And then once you identify that claim, then we write our two hypothesis statements. The first one is the null, and it is always an equality statement. So it would be either the mean equals some number or the proportion equals some number, depending on whether you're testing a mean or testing a proportion. Now, it does look slightly different when you have two populations that you are testing, that you're testing the difference between the two, but we'll get into that in a later video. And then your alternate statement is H1. You can also say HA. It is always an inequality statement. So it's either that the mean is less than, greater than, or not equal to some number, or it is, oops, I wrote H0 there, it should be H1. It is the proportion is less than, greater than, or not equal to some number. And then if you'll recall the numbers in the two hypothesis statements, they need to match. And so then once you write that out and you review what you're testing, you need to decide which type of test you are running. And so I have ZT and proportion. So basically you have I'm just going to call it a mean Z, or you could choose a mean T, or you could choose proportion. And all of these are, in Rguroo, is an inference. So you would choose mean inference if you're testing a mean, and you would choose proportion inference if you are testing a proportion, and then you would choose one population, at least for the ones we're doing in this section. And then once you do that, then if you're testing a mean and you're doing a mean inference, you have to decide whether they've given you the population standard deviation or whether they have given you the sample standard deviation instead. If it's a population standard deviation, we use the Z statistic, and if it's a sample standard deviation, we go with T statistics. I'm going to write that down. So mean Z is when population standard deviation is known or given, and a mean T is when the sample standard deviation is known, or perhaps they didn't tell you what the sample standard deviation is, but they gave you the data from the sample and you could calculate it yourself. The other thing with type of test is left-tailed, right-tailed, and two-tailed. So let's just draw an illustration of what each of those look like. Left-tailed, right-tailed, and two-tailed. All right, so left-tailed happens if your H1 is less than some number. And I should probably do a different color here so you can differentiate. Right-tailed is when your H1 is that it is greater than some number. And then two-tailed happens when you're not specifying whether it's less than or greater than you're saying it could be either one as long as it's different than some number. So if the H1 is less than, we consider that a left-tailed test. If H1 is greater than, we say that's a right-tailed test. And if H1 is not equal to, we say that's a two-tailed test. All right. So that's the types of tests. Now, in step 4, you're going to enter the information into Rguroo, and I have 3 different boxes popped up with instructions underneath each one to remind you what you need to include for each of these. So if you're testing a mean and you know the population standard deviation, you choose a mean inference. All right, you choose a mean inference right there. And you enter the sample mean, the population standard deviation, and the sample size. You include a variable label of the mean that you're testing. So like if you're testing the mean weight of babies who are just born, then you would type in that context, the mean weight of babies that are just born. And then you'll need to enter a significance level. If the significance level is given, you put in whatever that says. If it's not given, you assume that it's 0.05. And then you need to put in the inequality symbol and the number for the alternative hypothesis for your H1. So this right here is H1. And then make sure that you check Z statistic. So again, you enter sample mean, population standard deviation, sample size, label the variable, significance level, alternative hypothesis, Z statistic. That's what you enter into the box if you know the population standard deviation, which makes sense because if you know the population standard deviation, that's where you would put it. Then you would hit the preview button, and that would give you the p-value. It would run the test and give you the p-value. Now, if you know the sample standard deviation instead, so over here, we knew the population standard deviation. On this one, we know the sample standard deviation, or we have the info that we could get the sample standard deviation. And again, we're testing a mean. So the same box pops up for both. The difference is you'd put in the sample mean, and instead of putting in a population standard deviation, you put a sample standard deviation and a sample size, label your mean context, and under test hypothesis, you enter your significance level, your alternative hypothesis, and you choose T statistic this time. T statistic this time. All right, so that's the big difference there. And then you hit preview. And then there's when you test a proportion. So if you're testing a proportion, you need to enter the sample size and label what it's a sample of, what the population is. The number of successes and what a success is, label that. You do not have to label failure. Proportion of a success will show up automatically right here once you fill these two in. And then once you label these, this will show up as well, so you don't have to do anything there. What you do need to do is you need to put in your alternative hypothesis and choose large sample Z and enter your significance level. Now, for any of these, I want you to notice there is a confidence interval tab. So you can actually find the confidence interval and compare the results of the confidence interval to your results of your hypothesis test all at the same time, which is one of the great things about Rguroo, is that it's kind of a one-stop shop. You don't have to do separate calculations. You can do it all at one time. Anyway, so once you enter the info in the box, you are going to choose or click the preview button, which is the eyeball at the top, and on the next screen when that pops up, you're going to look for p-value. All right. So your p-value, let me show you. Both of these, these two graphs here show the observed and standard normal z-scale version of your test graph. And so basically, what happens is, okay, so this number here, that is your observed sample statistic. Over here, it looks like it's in the same place, but you have different numbers on the bottom. And the difference is this value here is your sample statistic, so either your sample proportion or your sample mean. Over here, it's if we converted it to a z-score on a standard normal curve, and it would go here. Now, what happens is if it's left-tailed, it finds the probability to the left. If it's right-tailed, it finds the probability to the right. If it's two-tailed, uh, the shadings on both sides, right? So for p-value, though, we go from the observed value or the z or the test statistic, which is what it's called when you convert it. And you measure the shading, which represents the probability of this occurring. And the probability of getting, in this case, 0.25 is shaded here, and that is your p-value, the 0.13762. So for this particular test that I have a picture of, we're saying that the probability, if the null is really true, that you would get a sample statistic as extreme as 0.25, that would be 0.13762. So then what we do is we decide, is that a really low probability, making this an unusual event or not? Well, this isn't unusual because it's not smaller than 0.05 or smaller than whatever the significance level would be. Significance levels are usually no bigger than 10%. They're usually 10% or less. So because this is bigger, we say, well, this is a likely outcome. And so if this is a likely outcome, with the assumption that the null is true, we don't have enough evidence to reject the null. And if we can't reject the null, then we don't have enough evidence to support the H1 claim. All right, so here is what I just said, but written out. You're going to compare the p-value to significance level. Again, you usually define that in the problem, but if they don't, assume that it's 0.05. And if your p-value is less than your significance level, reject the null. If your p-value is greater than the significance level, fail to reject the null. Let me also put this in here because sometimes I know people have trouble comparing numbers that are less than 0 to one another. They have a hard time with place value. So let me just say this. If p-value minus the significance level is less than 0, meaning, and let me rewrite that less than sign. If it's less than 0, that means it's a negative number when you subtract. That would be a way to tell that the p-value is smaller. And in that case, we would reject the null. All right. So this is just, if you have trouble comparing, like, let me just show you, like if the p-value is 0.007 and the significance level is 0.05. So I can tell you the p-value 0.07 is less than 0.05. It is less. But you may look at it and you might look at the 7 and you think, oh, the 7's bigger than the 5, so 0.007 is bigger. It's not. And the thing here is this is 7 in the thousandths place. This is 5 in the hundredths place. This is, it's basically, if we made them both go out to the thousandths place, now look at it, 50 is definitely bigger than 7, right? But let's say you have trouble with that. So what you can do is you have to do p-value first, and in your calculator you can do 0.007 minus 0.05, okay? And so you just pull up Desmos, and 0.007 minus 0.05, and look what we get. We get a negative number. We get a negative number. We get, oops, just give me a moment for this to pop back up. So when we subtract 0.007 minus 0.05, we get negative 0.043. And the whole point in that is I'm not necessarily interested in the 0.043 for anything other than this is what I'm interested in. I'm interested in that symbol. If you get a negative number, then that means the p-value is less, and that means you are going to reject the null. That is your decision. Now, if your p-value minus the significance level is greater than 0, meaning it's positive, all right, in that case, then that means the p-value is bigger than the significance level, and you would fail to reject the null. All right, so you don't have to do that subtraction. I just put that in there because I know some people have trouble when they are comparing decimal numbers. And so I wanted to put that in there to help you out. You can just quickly subtract p-value minus significance level. If it's negative, reject the null. If it's positive, fail to reject the null. And then in the previous video, I gave you guys a template to write out the conclusion statement. So if you reject the null, you say there is enough evidence to support the claim that, and then the claim is H1 in context. So you can't just say there's enough evidence to support H1. Or let's say H1 is that the mean is greater than 20. You can't just say there's enough evidence to support that the mean is greater than 20. You need to put it in context. You would say, let's say the serial problem we did in a previous video. There is enough evidence to support the claim that the mean serial weight is greater than 20 ounces. So you have to put it in context. That's very important. You can say support the claim. You can also, instead of support the claim, you could just say conclude that instead. So you can say there is enough evidence to conclude that and then put H1 in context. It's up to you. Either works. Instead of saying there is enough evidence, you could say there's sufficient evidence. That's another way to say it. Instead of saying there is not, such as right here, there is not. So when you fail to reject, you say there is not enough evidence or there's insufficient evidence to support the claim that, and write H1 out in context. Or you could say there's not enough evidence to conclude H1 again in context. And the reason that we make these decisions again is so again, what we're doing is we're assuming that H1 is true until we prove it. And I said that wrong. We're assuming H0, the null, we're assuming the null is true until proven otherwise. So again, innocent until proven guilty. That's our assumption going into the test. We collect our evidence, we run our test, and we get our p-value. So the p-value again is if H0, if the null is really true, how likely is it that we would get the sample statistic that we got? If it's very unlikely, having a low probability, so lower than the significance level, we say, well, if it's so low, that means it's unlikely to happen. And if it's really unlikely to happen, but it did happen, right, that must mean that our assumption was false to begin with. And if our assumption's false, we can reject it. So that's where we reject the null. And if our assuming that the null is true and we get our sample stat, if the probability of that occurring given that the null is true, or assuming that it's true, if that probability is bigger than our significance level, then that means it is a likely occurrence. And if it's likely to happen, when the null is equal to what we're saying it's equal to, then you don't have enough evidence to reject it. I mean, you can't say it's true, but you definitely can't say it's false. And if you can't say the null is false, then you can't say the H1 is true, because remember, those are contradictory statements and you can't say they're both true at the same time. So if you can't say the null is false, then you can't say H1 is true. So that's why when you fail to reject the null, you say there's not enough evidence. All right, moving on to some examples. Let's just jump in. We have example 1, Facebook time. A study by Webmetrics firm, I'm sorry, let me read that again. A study by the Webmetrics firm Hitwise showed that in August 2008, the mean time spent per visit to Facebook was 19.5 minutes. Assume the standard deviation of the population is 8 minutes. Suppose that a simple random sample of 100 visits in August 2009 had a sample mean of 21.5 minutes. A social scientist is interested in knowing whether the mean time of Facebook visits has increased. Conduct a hypothesis test to determine this. Use a significance level of 0.05. So let's first identify our claim. And it has to do with a social scientist here. The social scientist is interested in knowing whether the mean time of Facebook visits has increased. Increased from what? So increased from what it was back in 2008, which was 19.5. So we're going to start by writing our null and our alternate statement. We are definitely testing a mean here. Mean. So we're going to use mu for our symbol. And if you will recall, null is always equals. So equals what? We're assuming that it equals what it equaled back in 2008, which is 19.5. And that's our assumption until we prove otherwise, if we're able to do so. And then the social scientist is interested in seeing if it has increased. So increased would be greater than. So this is definitely going to be a right-tailed test. It's going to be a right-tailed test. So now we also need to decide which kind of inference we're doing. We're definitely doing a mean inference. And we need to look at our standard deviation and figure out which kind they gave us. Did they give us the population standard deviation or the sample standard deviation? So if we look, it says the standard deviation of the population is 8. So they gave us the population standard deviation. So because they gave us the population standard deviation, we're going to use the Z statistic when we run the test. So we need some input values. So things that it's going to ask when we use Rguroo is going to ask for sample mean. And the sample mean was, it says, suppose a simple random sample of 100 visits in August 2009 had a sample mean of 21.5. So X bar is 21.5. And then it's going to ask for the sample size. So the sample size is 100 visits. And then it's going to also ask for your population standard deviation, which we already said was 8. And then it's going to ask for a significance level, and they did give that to us. Significance level is 0.05. Okay, and I think that we're good there. We have everything we need. We need the X bar, we need N, we need sigma, we need the significance level, and we need the alternate statement, which we have. We have all of those things. So I'm going to move over to Rguroo, and we're going to click Analytics, choose Analysis drop-down, and choose Mean Inference, one population. And then we're going to put in our sample mean, which we said was 21.5, and population standard deviation, because that's what they gave us, is 8. And sample size is 100. We need to make sure we label our variable. So this is the mean the mean time of Facebook visits. So the mean of Facebook visit times. And let's do click over to the test hypothesis tab. The significance level is staying 0.05, and our alternate statement is that we believe that it is greater than 19.5, and we're going to choose a Z statistic. While we're doing this, I'm going to go ahead and do the confidence interval as well, because I think it's great that Rguroo will do both at the same time, and it will allow us to make some connections between the confidence interval that it gives us and the hypothesis test. So I'm going to click on Z statistic. For the confidence level, since we did 0.05 for the hypothesis test, I'm going to do 0.95 for the confidence level, and then hit the preview. And so lots of things going on here. All right, so first off, at the top, they give us, they tell us what we typed in. We typed in a sample size of 100, a mean of 21.5, population standard deviation of 8. You want to double check and make sure all of that is accurate. Here it says the alternative hypothesis, they call it HA, we've been writing H1, is the mean of Facebook visit times is greater than 19.5, and that is what we are trying to say. We did a 5% significance level, and so here they have the sample mean, which was 21.5. They have a standard error, so if they calculated that, you get 0.8. If I converted my sample mean into a statistic, it would be a Z statistic. It would be 2.5. And then we want to go over here to the p-value. That's really what we're interested in. And if you want to see the p-value graphed, you can see it here. So if we have 21.5 falls here, the probability of that occurring, given that the null is equal to 19.5, it looks like it's a pretty small probability, very small amount of shading. And again, that is 0.0062 if we rounded to 4 decimal places. So the p-value is 0.0062. Okay. So there we have that. Now I'm going to come down here and I'm going to write down kind of to the side the lower and upper boundaries of the confidence interval. So 19.9 to 23.1. And we'll revisit that in a moment. So I wrote that right here. All right. So going back to the p-value, I'm comparing the p-value to the significance level. The significance level is 0.05. I'm going to look at this and I can tell you that 0.0062 is less than 0.05. If you're not certain, let's type it in here. 0.0062 minus 0.05. I got a negative, which means it's less. And if it's less, the decision that we make is reject the null. So that's my decision. I am rejecting the null. So you want to write that out. You want to write that we are rejecting the null. And then once you do that, then you're going to write your conclusion. And so if you'll recall, if we reject the null, we say there is enough evidence for H1. So here's my conclusion. There is enough evidence to conclude H1 is true, right? So what was H1? H1 in context is that the mean time of Facebook visits is more than 19.5 minutes. You could also say there's enough evidence to conclude that the mean time of Facebook visits has increased, because that's kind of how it was worded in the problem there. All right. And again, I just want to go over, how do we know? All right. So if we reject the null because the p-value is small, we're saying that's not true. And if that's not true, then that must mean the other statement is true. So we can conclude H1. That is why there is enough evidence. All right. Now let's go over here to our confidence interval, and let's see if this agrees with our conclusion. So comparing this to our 19.5, this whole thing is greater than 19.5, the whole confidence interval. So that means we've estimated the true mean to be greater than 19.5, which is the same thing as what the conclusion states. So it agrees. Again, because the entire confidence interval is greater than 19.5. Okay, let's do another one. Average male height. According to the National Health Statistics reports, the mean height for U.S. men is 69.4 inches, and the population standard deviation is 2.84. In a sample of 300 men between ages 60 and 69, the mean height was 69.0 inches. Public health officials want to determine whether the mean height for older men is less than the mean height for all men. Conduct a hypothesis test to answer this question. So here's our claim. We want to know if the mean height for older men is less than the mean height for all men. So I guess they want to know is, as you get older, do you shrink, right? So based off of this, I'm going to write the null and the alternate statement. We are talking about mean here, so I'm going to use a mu. Null is always equal. So what is the mean height that we assume for all men? And that is this 69.4. And then we want to know if for older men it's less than that. So for the alternate statement, we put less. So this is going to be a left-tailed test. So I'm going to write that here. This is left-tailed. So when you do this in Rguroo, you're going to see shading to the left. All right, so we are doing a mean inference, and we need to see what kind of standard deviation did they give us. They gave us a population standard deviation. They actually used the wording. So if they give us a population standard deviation, we're going to do a z. And here are the things that we need. We need x bar, we need sigma, we need n, we need significance level, and we need the alternate statement, which we already have. X bar is the sample mean. So the sample mean for the 300 men that are between 60 and 69 is 69.0. The population standard deviation we said was 2.84. They sampled 300 men, and the significance level, they don't give us one. So if they don't give us one, you assume that it is 0.05. 0.05. All right, so we jump over here and we go to analytics. In the analysis dropdown, choose mean inference 1 population, and we enter our sample mean, which was 69.0, and the population standard deviation is 2.84, and our sample size is 300, and we're doing the mean height of older men, and then clicking on test hypothesis, we want a significance level of 0.05, and we're saying that we believe that it is less than 69.0. 0.4 for the alternate statement, and we're going to click Z statistic. And at this point, I can just hit the preview, but because I want to do the confidence interval and make connections there, I'm going to go back and hit confidence interval and hit Z statistic. And since the significance level is 0.05, I'm going to keep this at 0.95. Okay, so skipping to the part we need, we just need the p-value, which is 0.00735, which rounds to 0.0074. And then just for later use, I'm going to skip down to the confidence interval at the bottom. We get 68.7 and 69.3. All right, so here we go. We're comparing this to 0.05, and this is definitely less. If you weren't sure, again, 0.0074 minus 0.05, you get a negative number. And if it's negative, that means it's less. If it's less, we are going to reject the null. So we're rejecting the null again. And if we reject the null, we have enough evidence to conclude H1. So we would say, conclusion, there is enough evidence to conclude that, and then you got to put H1 in context. So you can't just say there's enough evidence to conclude that the mean is less than 69.4. We need to say there is enough evidence to conclude that the mean height of older men is less than 69.4 inches. You could also say there's enough evidence to conclude that the mean height of older men is less than the mean height of all men, because that was how it was worded in the question earlier. Now, going over to our confidence interval, we would say we are 95% confident that the true mean height of older men is between 68.7 and 69.3. So, is there evidence to suggest that it is less? Is there evidence to suggest that it is less than 69.4? Well, look at this. 68.7 to 69.3. This entire thing is less than 69.4. So what we do is we kind of compare it to the number in the null and the alternate statement and see how it compares. It's either going to be the whole thing is less, the whole thing is greater, or that number falls in between your two boundaries. And since this whole thing is less, that is what we said over here. We said that we believed that there was enough evidence that shows that the mean is less than 69.4, and our confidence interval is also showing that it's less than 69.4. So this is in agreement. We make the same exact conclusion both ways. Okay. Let's do another one. Example 3. Are children heavier now than they were in the past? The National Health and Nutrition Examination Survey taken between 1999 and 2002 reported that the mean weight of 6-year-old girls in the U.S. was 49.3 pounds. Another NHANES survey published in 2008 reported that a sample of 193 6-year-old girls weighed between 2003 and 2006 had an average weight of 51.5 pounds. Assume that the population standard deviation is 15 pounds. Can you conclude that the mean weight of 6-year-old girls is higher in 2006 than in 2002? So here's our claim. And when we write the null and the alternate statement, we're doing mean. So mu. H0 is always equals. So we're going to assume that the weight is what it was in 2002, which was 49.3 pounds, because they're saying, can you conclude that the mean is higher in 2006? So in 2006, they took a sample. They explained the sample is 193 6-year-old girls, and their sample mean weight was 51.5. And so we want to know if that sample can show us that the weight has increased. So it's greater than 59.3. So this is definitely right-tailed because it is greater than. All right, we're doing a mean inference, just like before. They give us the population standard deviation. So we're doing a Z again. They're going to ask us for some info. They're going to want X bar, sigma, N, significance level, and alternate statement, which we've already written. And so those numbers are sample mean was 51.5 because this is the mean for the sample of 193 6-year-old girls. So N is 193. The population standard deviation they said was 15. And alpha, the significance level is 0.01. So that's actually a little bit different than what it has been in the past because we've been doing 0.05 every time. All right, so now we're going to go and do our test. All right, analysis, drop down, choose mean inference 1 population, and our sample mean is 51.5. Our population standard deviation is 15. Our sample size is 193. We need to label our variable, and our variable is the mean of 6-year-old girl weights. And then I'm going to click on the test hypothesis tab. I'm going to change significance level to 0.01, and we're trying to see if it has increased. So if it's greater than the null, which is 49.3, and we're choosing Z statistic. And then I'm just going to go over confidence interval. And so if I did a 0.01 significance level, I'm going to do a 0.99. So I usually just try to make them add up to be the significance level and the confidence level add up to be 100. So I'm going to choose Z-stat there as well and preview. We're going to skip down to the p-value. The p-value this time is 0.0208. So 0208. And scrolling down, we're doing a confidence interval is between 48.7 and 54.3. All right, so if we're comparing this to our significance level, all right, so if you compare this to 0.05, the p-value, it is definitely, it's greater. Actually, no, I'm not comparing it to 0.05, am I? I'm comparing it to 0.01. So 0.02 is greater. If it was 0.05, it would not have been greater, but this is definitely greater. And if it is greater, that's when we fail to reject the null, because we're saying this sample mean that we got with the assumption that the null is true, this is likely. This is a likely occurrence. If the true mean is really 49.3, then getting a sample mean of 51.5 is could be a common occurrence. And because of that, we don't have enough evidence to reject this. And so if we can't reject that, that means we don't have enough evidence to support our H1. So we would say there is not enough evidence to conclude the mean weight of 6-year-old girls is higher than 49.3 pounds. And again, you can word it by saying there's not enough evidence to conclude that the mean weight of 6-year-old girls is higher in 2006 than 2002, because that would mean the same thing. So over here, looking at our confidence interval, we are 99% confident that the true mean weight of 6-year-old girls is between 48.7 and 54.3. This includes 49.3. 49.3 falls somewhere between 48.7 and 54.3. So if that's included, then we can't say that the mean doesn't equal that, because it could. And if we can't say the mean doesn't equal that, then we can't reject the null, which means there's not enough evidence to say that it's greater than 49.3. So again, these agree. They show the same thing, the same exact thing. I'm going to go back here and just show you when we did this at the top, it says the test is not significant at 1%. That means that we're failing to reject the null. If you look back at the ones where we did reject the null, it would say test is significant. So that's another way to double check. All right, moving on to example 4. The Bureau of Labor and Statistics reported that in May 2009, the mean annual earnings of all family practitioners in the United States was 168,550. A random sample of 55 family practitioners in Missouri that month had a mean earnings of 154,590, with a standard deviation of 42,750. Did the data provide sufficient evidence to conclude that the mean salary for family practitioners in Missouri is less than the national average? Use the alpha equals 0.05 level of significance. So here is our claim. The mean salary for family practitioners in Missouri is less than the national average. So from here, we're going to write our null and our alternate statements. And we're testing a mean here because, well, it says it right there. And we know that null is always equal. The alternate, most of the time matches up with the claim. The claim is that it's less than the national average. So the mean is less than whatever the national average is. So what is the national average? In 2009, it was reported the mean was 168,550 for the United States. So that's the national average. So 168,550, and the numbers have to match here. So our null is that it equals 168,550, and our alternate is that it's less than. Now, we are going to do a mean inference. And because we're doing a mean inference, we need to decide whether to use a z or a t, and that has to do with the type of standard deviation that they give us. So let's locate the standard deviation. It's right here. So let's read the sentence that it's in. A random sample of 55 family practitioners in Missouri that month had a mean earnings of 154,590 with a standard deviation of 42,750. So there are a sample of 55, and this sample in this sentence says that for these 55 families, the mean was this, and here's the standard deviation of 42,750. So this standard deviation is the standard deviation for this sample of 55 families. So that means it's a sample standard deviation. So because we know the sample standard deviation, we're going to do a t statistic when we run the test. So let's go ahead and write this down before we forget. 42,750. Our sample mean was, for this 55, was 154,590. The sample size, we need that. That was 55 families. Our significance level is 0.05. And I believe that's everything that we need. So let us switch off here to Rguroo, and we're going to go to Analytics, and we're going to go to Analysis, and then Mean Inference, one population, and we're going to enter each of our values here. Our mean for the sample was 154,590. Our sample standard deviation was 42750. And our sample size is 55. Notice we didn't put anything into population standard deviation. We left that blank. The mean of, we're testing the mean salary. Oops, I misspelled salary. Salary for family practitioners in Missouri. That's what we're testing. We're doing a hypothesis test at a 0.05 significance level that it is less than, and the alternate statement is 168,550. And just double check to make sure you type in everything correctly. And then remember, it's T statistic because we know the sample standard deviation. And we do the preview, and we get a p-value of 0.0094. And now we are going to compare that to our significance level. That is definitely less than 0.05. And so if it's less, our decision is to reject the null. Because if the p is low, the null must go. So if the p is smaller than the significance, we reject the null. So here we go. We're rejecting the null. That means we have enough evidence to support the claim. And I forgot to move it back over here so you can see that. So we rejected the null. I'll cross that off. That means we've got enough evidence for H1. So conclusion, there is enough evidence to conclude that the mean salary, so we have to write H1 in context. So the mean salary for family practitioners in Missouri is less than 168,550. You could also say it's less than the national average. It's up to you. Real quick, I'm going to go back to the basics box, and I want to go click on confidence interval and do a 95% confidence interval to see if it agrees. Don't forget to click T statistic. Oops. And preview. And then the confidence interval will be at the bottom here. So it looks like our lower boundary is 143,033. Upper boundary is 166,147. This entire confidence interval, let me go back to the other screen. This entire confidence interval, 143033 to 166147, what this is saying is that the true mean is falling somewhere between those two numbers. So the mean salary for family practitioners, we're 95% confident that the true mean salary for family practitioners falls between $143,033 and $166,147. 168,550, that whole confidence interval is less than that. So it agrees because it's less than 168,550, the whole thing. Okay. All right, moving on to the next one, baby boy weight. The National Health Statistics Report described a study in which a sample of 360 one-year-old baby boys were weighed. Their mean weight was 25.5 pounds with a standard deviation of 5.3. A pediatrician claims that the mean weight of one-year-old boys is greater than 25 pounds. Did the data provide convincing evidence that the pediatrician's claim is true? So let's find the claim. The pediatrician claims that the mean weight of one-year-old boys is greater than 25 pounds. We'll use that to write our null. In our alternate, we're testing a mean again. And for the alternate, the claim says that it is greater than 25, which means that null is equal to 25 pounds. We're testing a mean again, so it's a mean inference. And look at our standard deviation. The mean weight was 25.5 pounds with a standard deviation of 5.3. The mean of what? It says their mean weight, and it's the mean for these 361-year-old baby boys that were sampled. So this here is a sample standard deviation. So we're going to do a T because sample standard deviation was given. All right, so let's write down our stats. We have X bar, which is sample mean, sample standard deviation, sample size, sigma. Sample mean was 25.5. Standard deviation for the sample is 5.3. Sample size was 360. So we've got sample mean, sample standard deviation, sample and the sample size in, and sigma is 0.01. All right, so we have everything that we need. So we can go back over here and analytics, analysis, mean inference, one population. And our sample mean was 25.5. Our sample standard deviation is 5.3. We don't know population standard deviation. Our sample size is 360. Our variable label is the mean weight of 1-year-old baby boys. And we're going to do a hypothesis test. Okay, here we go. At a significance level of 0.01, so you want to change that to match up with that, 0.01. And our hypothesis is that it is greater than 25 pounds, and we said we're using a T. And while we're here, I'm going to click on the confidence interval tab. Click T statistic, and then if I do 0.01 significance level, I'm going to do a 0.99 confidence level. And I'm going to write down the p-value on my other screen. You can't see it yet, so just bear with me. I'm copying it off of here. 0.0372. All right, and if you're asked for the test statistic, it's right here. Oops. Only meant to highlight this one thing here. I highlighted everything. This 1.7. Oops. This. It gets happy with a highlighter. So this first part that I highlighted, the 1.789997, if they ask for the test stat, that's it. But we want the p-value over here on the end. You can also get it down here from this graph. Oh, I'm going to go ahead and write down the confidence interval too. I'm going to write that down. The confidence interval goes from 24.78, I'm going to just round it 2 decimal places, and 26.22. Okay, so going back to the other screen. All right, so what we're saying is that the p-value is 0.03. 0.0372 is greater than 0.01. It's greater than the significance level. So because it's greater than the significance level, we're going to fail to reject the null. And if you can't reject the null, so I can't reject this here. I can't reject it. So if I can't reject that, then I don't have enough info to support the second one, the alternate statement. So if you can't reject the null, we're going to reject the alternate. And so in terms of the alternate, we would say there is not enough evidence to conclude H1 is true. What is H1 in context? It is that the mean weight of 1-year-old boys is greater than 25 pounds. So there's not enough evidence to conclude that the mean weight of 1-year-old boys is greater than 25. There's not enough evidence to conclude that. Now, looking up here, 25 is included in the confidence interval. It's somewhere between 24.78 and 26.22. What that means is that it agrees with the conclusion that there's not enough evidence to say that it's greater than 25. So if you look here, it agrees with that because you can't say that it's greater than 25. It could be as high as 26.22. It could be as low as 24.78. So because it's somewhere in between there, you can't say that it is definitely going to be over 25. So so this agrees with the conclusion that it's not greater than 25 because 25 was included. Okay, so that's example 5. Moving on. Example 6, commute time. In 2007, let me try again. A 2007 Gallup poll sampled 1,019 people and asked them how long it took them to commute to work each day. The sample mean one-way commute time was 22.8 minutes with a standard deviation of 17.9 minutes. A transportation engineer claims that the mean commute time is greater than 20 minutes. Did the data provide convincing evidence that the engineer's claim is true? 0.05 significance. Here's the claim. Transportation engineer claims that the mean commute time is greater than 20. So, null. Alternate. We're doing the mean commute time. That is greater than 20. So that would be your alternate statement. And then for our null statement, we would say that it is equal to 20. Equal to 20. And then we're doing a mean inference again. And then checking out the standard deviation. The sample mean, 22.8 minutes with a standard deviation of 17.9. So this is definitely a sample standard deviation. So we're doing a T again because sample standard deviation was given. All right, so let's enter our data. So X bar, sample standard deviation, sample size, sigma. So X bar is 22.8. Sample standard deviation is 17.9. N is 1,019 people. alpha, I think it said sigma, alpha is 0.05. This notation is alpha, not sigma. So if I said that, I apologize. Okay, so we have everything that we need. So let's go back here and we'll go to analysis under analytics, mean inference, one population. Sample mean is 22.8. Sample standard deviation, 17.9. No population standard deviation. Sample size is 1019. Labeling the variable, it's the mean commute time. And since it's a 0.05 significance, I'm going to go ahead and hit the confidence interval for 95 and t-stat under test statistic. Significance level is 0.05, and we're saying that it is greater than 20, and we're doing t-stat. Preview. All right, looks like now this one, because I went ahead and clicked confidence interval, the confidence interval is right here. I'm going to go ahead and write this down. We're saying the commute time is between 21.7 and 23.9. So that looks like it is definitely, this is showing, the confidence interval is showing that it's greater than 20. So let's see what the hypothesis test shows. Let me just find the p-value here. So the p-value is 3.489, but there's an e. So 3.4, we'll just say 3.49 e negative 7. So that means, let me go back to the other screen. So what that means is this is really moving the decimal over 0.0000003. And that is definitely less than any significance level, in this case 0.05. It's definitely less. So if it is less, we're going to reject the null. And so if we reject the null, we would say there is enough evidence to conclude the mean commute time is greater than 20 minutes. And we said up here, this whole thing is greater than 20, so that means this agrees. All right, so we've done examples 1 through 6. I'll do a few more. Let's do example 7. A nationwide survey of working adults indicates that only 50% of them are satisfied with their jobs. The president of a large company believes that more than 50% of employees at his company are satisfied with their jobs. To test his belief, he surveys a random sample of 100 employees, and 54 of them report that they are satisfied with their jobs. Can he conclude that more than 50% of employees at a company are satisfied with their jobs? Use the alpha equals 0.05 level of significance. So can he conclude that more than 50% of the employees at the company are satisfied with their jobs? That's the claim. So this time, notice we're not testing a mean. They're talking about percentages, so we're testing a proportion. So we're going to use a capital P rather than mu. He's saying that it's more than 50%. So instead of writing 50%, I'm going to write 0.50 and put it in as a decimal. So there's my null, is that the proportion is equal to 0.50, and H1, the proportion is greater than 0.50. Now, this time I'm going to do a proportion inference instead of a mean inference. And it's going to ask for a few things. It's going to ask for sample size and then the number of successes. And then it's going to ask us to label these. So let's see. The sample size is 100 employees. And 54 of them report that they are satisfied. And I'm writing those labels down because you have to put labels in for this. And then outside of that, the only other thing that you need is your significance level, I believe, which is 0.05. And we're going to do a confidence level of 95%. We'll go ahead and find the confidence interval as well. So let's go here. So still under analytics analysis, you're going to do proportion inference this time, one population. And you're going to go down to data and skip these drop downs here. You can't really drop down and choose anything because we're not using a data set. And just go over to where it says sample size. And there was 100 employees. So you have to label it. The label goes before it. So factor label, put employees. So 100 employees, and under number of successes, we'll say 54 of them said, and then for the success label, they said that they were satisfied with their jobs. So you can just leave it as satisfied or put satisfied with jobs. All right. I think we said we're already going to do a 95% confidence interval. If you would like to do a confidence interval with this, you're going to choose large sample Z. And then for the alternate statement, we're choosing greater than 50%, so that's greater than 0.50. And again, choosing large sample Z. Significance level is 0.05, and voila. One moment, looks like it logged me out. Okay, so try this again. All right, so at the top it gives you counts to make sure, you know, how many were satisfied with their job. And then it calculates based off the total how many others. So basically those not satisfied with their job. So it fills that in for you if you were interested in that info. But what we want to look at is our p-value here, which is 0.2119 if I were to round. So I'm writing that down on the other screen that you can't see, so just give me a second. Okay, and then while we're here on this page, I'm going to go ahead and give the lower and upper level for the confidence interval, which is between 0.4423 and 0.6377. All right, going back to the other screen. Okay, so p-value, we're comparing that to 0.05. It is greater, so if it's greater, we fail to reject. And if we fail to reject, we can't throw the null out, which means we have to throw the alternate out instead. So if we're throwing out the alternate, that means we don't have enough evidence to conclude it. So there is not enough evidence to conclude that more than 50% of employees at the company are satisfied with their jobs. And then looking here, this whole thing, can it conclude that it's more than 50%? No. .50 is included. So if it's included, that means that you don't have enough evidence to say that it's greater than 50. So this agrees again. All right. Let's move on. Spam. According to Message Labs Ltd., 89% of all mail sent in July 2010 was spam. A system manager at a large corporation believes that the percentage at his company may be 80%. He examines a random sample of 500 emails received at an email server and finds that 382 of the messages are spam. Using a significance level of alpha equals 0.05, can you conclude the percentage of emails that are spam differs from 80%? So there is the claim that we're working off of. We are testing a percentage, which is a proportion. We're saying that it differs. That's what the last sentence says, that we're trying to conclude that it differs from 80%. So I'm going to do 0.80 instead. That means the null is equals that same number. So when they say differs, we use the not equal to sign, and it makes it a two-tailed test instead of a one-tailed test. Okay, so we're doing a proportion inference. So let's write down what we know. We know the sample size is 500 emails. Received. And then of those, I'm calling this the number of successes, we call that X for short. That's 382 were successes, and they were messages that were spam. And significance level is 0.05. And I think we're good again. So let's go back here. Analytics, analysis, proportion, inference, one population. Sample size 500 and 500 what? Label it emails. And the number of successes was 382. 382 emails were spam. And you can label failure if you wanted to. You could label that as not spam, but you don't have to. Always choose large sample Z for these. I'm going to go ahead and do the confidence interval of 95%. And we're saying that it's not equal to 80%, so 0.80. Choose large sample Z here, and 0.05 significance. Preview. Let me go ahead and write down the confidence interval on my other screen. So you guys write it down to 0.8012, 0.0744, and the p-value is 0.0442. All right, let's go to the other screen. You can see where I wrote everything down. Real quick, let's look up and see what the confidence interval is telling us. The confidence interval, the whole thing is greater than 0.80. So let's see what the hypothesis test shows. So 0.0442 is less than 0.05, not by much, but it is less. And if it's less, then we reject the null. And if we reject the null, that means there is, so let me reject it. Reject. There is enough. Oops. Let me try this again. There is enough evidence to conclude that the percentage of emails that are spam differs from 80%. All right, and this agrees because it's saying that it's greater than 80, which differs. So the whole thing is greater than 80%, and that's a way to be different. So it agrees that it differs. All right, example 9. A marketing manager for a cell phone company claims that more than 35% of children aged 10 to 11 have cell phones. In 2009, survey 5,000 children aged 10 to 11 by MediaMark Research and Intelligence. 1,805 of them had cell phones. Can you conclude the manager's claim is true? So we conclude that the manager's claim is true. What is the manager claiming? He claims that more than 35% of children aged 10 to 11 had cell phones. And we're testing a percentage, so we're doing P again instead of mu. And, oops, we're saying 35%, but he's claiming that it is more. And honestly, I should go ahead and write these instead of percentages. I should write them as proportions, 0.35. So greater than 0.35 for the alternate and equal to 0.35 for the null. We're doing a proportion inference. The sample size was 5,000 children aged 10 and 11. And then our successes, 1,805 of them were successes, and the successes had cell phones. That's what a success was. Significance level, alpha equals 0.01. And that's all we need. So, analysis, proportion inference, one population. All right, sample size was 5,000. And this is children aged 10 to 11. There was 1,805 children who had cell phones. If you wanted to fill in failure, they did not have cell phones. But success was had cell phones. And if we want to do 0.01, I would do a 0.99 confidence level. Large sample Z. Hypothesis is that it should be greater than 0.35. Large sample Z, 0.01. Significance. All right. And the lower and upper boundary for the confidence level is 0.3435 to 0.3784. All right, and p-value (0.0515). Okay. All right, so 0.05 is greater than 0.01. Before we do that, let me go back to the confidence interval up here. So the confidence interval, this includes 0.35. So it's not showing that it's greater. So it's not greater than 0.35. All right, so let's see what the hypothesis test says. It says that the p-value is greater than 0.01. So if it's greater, then we fail to reject the null. And if we fail to reject the null, we have to reject the alternate. So we would say there is not enough evidence to conclude that more than, and we always have to do this in context, right? More of H1, more than 35% of children aged 10 to 11 have cell phones. And then, again, our confidence interval agrees because it's saying with 99% confidence that the true proportion of children aged 10 to 11 who have cell phones is between 34.3435, which is around 34%, and 37.84%, or as a proportion 0.3784. 0.35 or 35% is within that. So because 35 is included, 0.35, you can't say that it's greater than 35. The whole thing would have to be greater than 35% to agree with that, and it's not. To agree with the H1, that is. So this does agree with our conclusion that we don't have enough info or evidence to conclude that it's more than 35%. So they both show the same thing. Okay, so worked examples 1 through 9 with you. There are examples 10 through 18 that you can work on your own, and I would really encourage you to do so, to practice setting it up, figuring out what kind of test to run, running the test, getting the p-value, making your decision, and then from there writing your conclusion. And while it doesn't say to, I think it's a good activity, a good practice to go ahead and find your confidence interval as well, and see if you can figure out whether or not the confidence interval agrees with the conclusion that you made about your H1, and seeing if you can figure out if they agree, and if so, why. Okay, so that is all I have for you. If you end up practicing these questions, examples 10 through 18, I will have a set of notes with those worked out for you to check as an answer key in Blackboard. All right, thanks, and have a great day.